Video 7 for thermochemistry. I think I might sneeze. Okay, I guess I'm not going to. Anyways, so what we're going to look at now is Hess's law. It's another way to get the heat of formation. And basically what Hess's law is when the heats of formation are too difficult. So a couple of things we already talked about is that you can't just usually make compounds from elements. And if you look at your heats of formation chart, that's what you're always doing. You're taking elements and you make them, and that's how you figure out the heats of formation. But a lot of times you can't do that. Like, you can't make Tylenol from its elements. It's way too complicated. Sometimes reactions are too slow. They could take like a millennia. Who wants to wait? And sometimes they're just too dangerous, even though some people are pyros, but let's not kill ourselves. So in any of these situations, what we do is we use Hess's law. And I love Hess's law because it's like algebra with chemical reactions. So just be prepared. It's amazing. So here's an example of one that we're going to do. But the actual statement of the law is that if you do the reaction in steps, and actually lots of reactions are carried out in steps, what you can do is you can actually just sum them up like an algebra problem, cancel things out that are the same and stuff, and you get your delta H the exact same. So right here is one where we're making carbon monoxide. And theoretically, we could take a carbon and half an O2, and we would make carbon monoxide. But if you actually do that, you don't just get carbon monoxide, you also get CO2, and it doesn't really work that well. So this is a classic example of when we would use Hess's law because it's not something we can do easily in lab. So what we're going to do is, keeping in mind that this is what we want. We want this guy right here. What we have to do is use steps to actually get there. And I will tell you, typically on the AP test, they just give it to you, and I just give it to you. But this right here is in your notes, and this is what you do for when you need to find them. So like if you need to make things, like you can see here's the one for carbon monoxide, here's the one for CO2. And typically what you do, if you have to look up the reactions, what you're looking for is any compounds that you're making. You don't usually have to look up the elements because they typically just naturally happen. But like if you're making benzene, you need to look up the reaction of how to make benzene. And if you're making hydrochloric acid, you need to look up the reaction of making hydrochloric acid. So for this example, it's already given to you. These are the two steps they tell you need to do. But in case you have to look them up, that's how you do it. So what you do is you have your two steps, and then you start comparing them up here and say, okay, like what can they give us that we need? And if you look at the first one, it's not, they give us carbon and stuff like that. The oxygen is everywhere, so that doesn't really help, and we don't really want CO2. So if you look at this, the only thing we actually want from the first step is carbon. So what you do is you look at it and compare it to what you want. And you say, is carbon on the right side? And does he match? Like, is there 3 carbons and 3 carbons? And this one, he's on the right side, and we even have the same amount. So the first step here is okay as is. So what that means is we don't have to do anything to the first step. This guy right down here, I just rewrote him. The second reaction here, again, CO2 we don't really want. There's lots of oxygen all over the place. So the thing we want out of this reaction is carbon monoxide. And again, you're trying to find the thing that is unique to the reaction. Again, it's typically not elements. I know this one had an element in it, but most of the time it's not the elements. Most of the time it's going to be those unique compounds. So like carbon monoxide is our unique compound here. And what you see here is we have enough carbon monoxides. We have 1 carbon monoxide on the left and 1 carbon monoxide on the right, but he's on the wrong side. So what we need to do is we need to flip the reaction. So instead of carbon monoxide being a reactant, we need to make it be a product. And what that means is I flip the reaction, and you can see it's flipped down here. And what that means is that instead of negative 283 kilojoules per mole, I need to make it positive 283 kilojoules per mole. So you just do that because you're perfectly allowed to. And then the last thing we have to do is add them up algebraically. The whole cool thing about Hess's law is that when I add up these equations, I better get this equation up here. If I don't get it, I didn't do the thing right. So what you do is you can see I made a mark on either arrow, and I look for anything that's the same on both sides. So you can see that there's a carbon dioxide on the left, There's a carbon dioxide on the right. It's completely mathematically redundant. Cross them out. They disappear. And then you can see on the left we have a whole oxygen. On the right we have a half oxygen. So we can get rid of a half oxygen on each side. And then what you're left with is one carbon, a half O2, and carbon monoxide. So as long as everything adds up to your original thing, that means that you did the problem right. And all you have to do is add up your delta H's. So you take negative 393.5, add it to 283.0, and you should get the delta H reaction for the specified reaction at the top. It's really cool. It's algebra of chemical reactions. I know, don't get too excited. It's amazing. It's awesome. You will love it forever. I know. So here's another problem where we're working through the same thing here. We want to calculate the standard enthalpy of acetylene from its elements. So the first thing you have to know is, okay, what does that even mean? So obviously, like in the AP problem or on the test, I would tell you what acetylene is. Acetylene is used in welding and stuff, burns at a high temperature, but it's C2H2 and it's a gas. So that's what we're going to make. If we would make acetylene from its elements, we would have 2 carbons and a hydrogen gas, and that's what we would make. However, that's not what we have. So we have these 3 reactions here, and we need to use them to actually make the acetylene. So again, you look at each of these reactions and say, okay, what are they going to do for me? So if you look at the first reaction here, reaction A, the thing that's unique here is carbon. And you can see he's on the right side. He's a reactant, and that's what we want, but we need 2 of him. So what that means is we have to multiply the whole equation by 2. So we have 2 carbons, 2 O2s, 2 CO2s, and that means we need to multiply our delta H by 2 as well. If we look at reaction B, we have hydrogen. And you can see hydrogen is a reactant in B. He's also a reactant in what we want. And he's the same thing. So we don't have to do anything to B. We just write him out again. And you can see down here I didn't change anything to him. And then the very last reaction, we're making acetylene. So you can see here's acetylene. Here's our unique guy. Now he's on the wrong side, so we're going to have to flip him. And we only want 1 acetylene, but there's 2 here. So what I have to do is I have to flip the whole reaction, and if you look down here, I have to divide all my coefficients by 2. So what that means for delta H is I was negative 2,598.8. I have to switch my sign, so I end up being positive 2,598.8. And I divided the reaction by 2, so I'm going to divide it by 2. And what you have to get used to is you're allowed to control it. You're allowed to do things to it and change it and really see what you're making. So just make sure you have that written down. We'll go to the next slide. And then the next slide just shows you how we add everything up to it. So here I just have everything written out. I have everything that was on my reactant side, everything that was on my product side, and what I did is I crossed stuff out. That was the same. And you can see here that I do get my same reaction, which is good, because if I don't get that, that means I didn't do the Hess's law problem right. And then what I did is I used those delta H's from my new equations, and I found out that this is an endothermic reaction, and it's plus 226.6 kilojoules per mole to make some acetylene. Alright, this last problem is just one more example here. Now, one thing that's a little different here is they didn't give us the reactants, or the reactions. So it says we use phosphoric acid, and it's in soft drinks and all that other kind of stuff, and this is how you make it. So P4O10, water, and phosphoric. And we want to know how much heat do we produce if we have 1 mole of the solid P4O10. So here's the reaction that we're trying to match. Now, one thing, I already looked up the reactions and gave them to you here. But what you're noticing here is when I looked them up, I made P4O10, and that's the reaction. I made water, that's the reaction, and I made the phosphoric acid, and that's the reaction. So take a second. I know they're already written here, but see that you understand them. Make sure they make sense. Try to work through the problem. You can pause it, the video if you want, and then the next slide when we come back, we'll have all the work on it so you can make sure. This is something that is not hard. Most people actually kind of sickeningly just quietly like Hess's law. But you have to do these a couple times because it's not usually something you're used to. You're not used to doing algebra of chemical reactions. Again, it's pretty cool and awesome, and I think it's really neat how it works, but you're not used to inherently doing them. Alright, and here is the answer. So you can see what you had to do, flip them in, all that kind of stuff, multiply things. Make sure it cancels, and then you should add up to your delta H, which hopefully is negative 370 kilojoules per mole.